So today's video I'm going to record lecture 43, and this is basically on least square fit, and I am Dr. Ranjan Ganguly. Now this least square fit is an extremely important topic because it helps you fit various functions or curves on data. And in fact, if you look at a large number of problems in what is known as data science, they essentially involve doing least square fits. So we are going to discuss this topic in the context of response surface methods, which are polynomials, but the methods are very general. The least square fit, as discussed in this video, is extremely general. So the method of least squares is used to find the regression coefficients in a multiple linear regression model, which we have discussed in the previous slide. Now, how you do this is that you generate data. And essentially, if you recall, we had these points x1, x2 to xk, which are the data points which go into the model. And then there is the point y which comes out of the model or the computational code or the experiment, as the case may be. And essentially now we run these experiments or run these simulations at these points x1 to xk and get an output y. And we do that n number of times. So this is for y1, we put in the values x11, x12 all the way to x1k, and out from the code comes y1. Similarly, we put in the value x21, x22, x2k, and the code or the experiment gives the value y2. And we continue this till n samples, and therefore we have xn1, xn2 to xnk as the values which go into your code or into your experiment, and then out comes yn. So at the end of this particular process, we have obtained n samples of this value y, and we have given n samples of this vector x. So in each of these cases, a vector x has been fed into the system and a scalar y has been brought out. Now we go back to the equation we had, and what we now have is that for each of these particular simulations which we have run, y1, y2 to yn, we get one equation for each of these values of I, and therefore we have all these equations here. So let us say we put some value of I here, then yi would be beta 0 plus beta 1 x, I1 plus beta 2 x, I2 all the way to beta k x ik. And this I would be varying from I is 1 to all the way to n. So these are essentially these n samples of data which are obtained by our numerical experiments or our actual experiments. So essentially this is the set of equations we now have, and what we need to do is get an estimate of these values of beta 0, beta 1 to beta k, and for that we will use the least square method. So basically what happens in least square is that we first form this function L, which is the summation I is 1 to n over all the epsilon I squares. And the epsilon I square is essentially the lack of fit at any one point between the prediction from the function and the actual model. So here this particular equation is used here, which we will recall is yi minus the model here, and we square this. And the reason this is squared is because the epsilon can be both positive and negative, and essentially we do not want it to deviate from 0. Therefore one of the ways is to simply square the epsilon value, and that gives us this equation or this expression here. Now we go back to our basic calculus or basic optimization. We want to find these values of beta such that this function L is minimized. So that is known as least square. And to do that, we know immediately that we need to differentiate L with respect to beta 0 and with respect to the beta j values. So first we differentiate with respect to the beta 0 values. So here you can clearly see that you get this equation here. So the 2 comes from the square term and you get a negative sign because of the presence of this negative before beta 0. And so that is something which we get here. Now, basically what we do is we put b0 and bj instead of beta 0 values to point out that these are the values obtained which are the best possible values, which essentially result in L becoming a minimum point. So these are known as the least square estimators, and these are b0, b1 to bk. These are actually the best possible values of beta 0, beta 1 to beta k. Now, this is one equation which you obtain. Of course, we know we set the gradient to 0, so this is set to 0. The next one we will obtain by differentiating L with respect to the beta j. So again, we take the L and we differentiate with respect to beta j. So this is this beta j here. Now again, there will be a negative 2 coming from the square and the negative sign here, and you'll get this back here. And then you need to differentiate this part. So this is going to throw xij at you. So essentially, this is the second equation, or rather I should say a set of equation, because now you obtain equations for j is 1, 2, all the way to k. And again, once you solve this system of equations in conjunction with the equation on the previous slide, you are going to get the values of b0, b1 all the way to bk, and then you are going to have a least square fit for the problem you are dealing with. So basically the whole problem of least square is to get these values b0, b1, b2, bk, and then we developed this fitted model here, which is y hat is b0 plus b1 x1 plus b2 x2 plus bk xk. And once you have got this fitted model, you essentially have your fit for the problem. Now actually it is simpler to work with matrices when we are doing this kind of least square fit. And so what we are going to do is we are going to rewrite this equation here, which was for the regression model, and then we are going to put it in matrix form. So essentially if we put it in matrix form, we get y is x beta plus epsilon, where all these are essentially vectors and matrices. Y is the set of samples y1 to yn. Beta are the values we need to find. So these are the coefficients, regression coefficients for the problem. And then epsilons are the lack of fit terms, epsilon 1 to epsilon n. And the interesting thing here is this X matrix now. And this X matrix comes because all the 1 terms here corresponding to the beta 0 coefficients, and the remaining terms correspond to the coefficients, for example, x11, x12 all the way to x1k, and next one will be x21, x22 to x2k, and there are n number of samples, so the last one will be xn1, xn2, xnk. Now remember that you already know these points x's and y. Therefore, you know this particular matrix X, and you also know this vector Y, because essentially you have selected these points at which you run your code or you perform the experiments. So essentially the Y vector, the X vector are known. The beta vector is not known. That's something we want to find. And the epsilon is also not known, except for the fact that it is possibly close to normal distribution or normally distributed. So now we are going to do the same problem as before with this function here. We are going to try to minimize the square of epsilon. So let us start with this equation here and then form the L value, and L would be now epsilon transpose epsilon, which is essentially the same as this. It is the scalar or dot product of these two vectors. And then from this equation we can write it as y minus x beta. So essentially we get this equation out here. we expand this equation out here. Now to do that, remember that whenever you have matrices in the form A B transpose, that becomes B transpose A transpose. So we have used that fact here. Now we multiply this matrix out, or these matrix vectors out, to get this equation. So the first term would be yty, then you would have a term negative ytx beta, then you have a term negative beta t xty, then you have a term positive beta t xt x beta. So 4 terms coming out of this multiplication here. Now one of the things we can do here is simplify this term. So we take this term here, that is beta transpose x transpose y, and we can take the transpose of this because all these terms are essentially scalars. And if we take the transpose, and again we use the fact that AB transpose is B transpose A transpose, therefore here we would get this thing going in front, so this would become xt yt beta tt, and so we get this here as y transpose x beta. So therefore we have two such terms, and therefore we can write L in this form here, that you have the yty term from here, you have minus 2 into beta t xty, and then you also have the last term here, beta transpose xt x beta. So this is the value or the function which we seek to minimize, and we seek to minimize this function to find the values of beta, which will essentially bring this L to a minimum. Now of course we know from calculus that we need to differentiate this L with beta and set that equal to 0. So again this is the function L written here again, and if we differentiate with respect to beta, this term will be decimated. The second term would be negative 2 xty because this beta is differentiated for, and the final term will have a 2 xt xb because there is a beta t beta or a square type of term here. So essentially this is something you get, and again as in the process we followed before, we replace the beta by b here, which essentially means the fact that this b here, which is the solution of this equation, corresponds to the optimal values of beta, and these are therefore the coefficients we will use for the fitted model. So from this equation I can simplify this equation here, so I get xt xb equals xty, and then the b coefficients can be written in this form. Now once again recall that the X matrix represented the entire set of points X which you use to obtain the vector Y. Therefore X and Y are both known, and therefore this particular calculation can be done very simply if you have any kind of numerical computation with you. For example, if you have MATLAB or Python, NumPy or something like that, you can very easily do this calculation, and at the end of it you have found beta, and therefore you have found the fitted regression model. So the fitted regression model is of course not an exact solution to the problem, because it's trying to fit all the points which you have given to the particular functional set which you have provided, and therefore there is going to be an epsilon present everywhere, and the epsilon can be calculated by y minus y hat. Y hat are those predicted values which you have obtained, y is the actual data which you have obtained. So this is really the actual value or the data you have provided to the least square system, and this y hat is actually the function you have got or the values you have got. So again there is going to be some deviation here, and then we can study this value further to see how good the curve fit is going. So let us make some comments on this process. Now one of the important things to do is to study the fitted response surface model to ensure that it provides a good approximation of the actual system. Now in many systems which are only of 2 to 3 design variables, and sometimes these are often presented in textbooks, we can actually plot the actual function values and the response surface on the same graph and see how well the fit is doing. And this is actually done in many places and books. Now, if you have a higher dimensional problem also, you can still do this by setting many of those variables to constant and just varying a couple of variables at a time. So this does give you a qualitative snapshot at the particular function. Now, for most real problems, such a comparison is not possible because you have too many design variables. So what typically one can do at this stage is look at this epsilon vector of the residuals. And this has a lot of information about whether the problem is good or not. We are going to discuss that in detail in our next video. But one of the important things is that the residual should approximately satisfy the requirements of a normal distribution. So this is something which is very important, and one should of course see if those are distributed on both sides of 0. So that is one check. And also it should not show any distinct pattern. So there should be some randomness in the distribution of these values. So again, this is the well-known least square fit. And like I mentioned before, this is not just used in response surface method, but in the entire important problem of curve fitting. And as you know, in many situations, curve fits are extremely important. And you can curve fit on any kind of function. It doesn't have to be a polynomial function. It can be something else. It can be trigonometric functions. It can be functions of sigmoid, or it can be piecewise linear functions, as it is done in deep learning situations sometime. So whatever your function may be, you always need to come back to this least square fit type of situation, and therefore it is a good idea to check out the least square method very well so that you can do all these kind of curve fits. So I will terminate this video here, and I will see you in my next video where we are going to study the residuals.